Okay, so good afternoon, ladies and gentlemen, and welcome to this session on nuclear power to those in the room and also to our viewers who are seeing this on a webcast. Time's very short indeed. I've been told we should finish by 4:30, so I'm going to have to ask everybody to be extremely brief because we want to have time for questions. I think everybody on the panel has spoken before, so I'm not going to introduce them, with one exception, which is Elisabeth Rachlew, who is a professor at the Royal Institute of Technology and a member of the Physics Class and Energy Committee of the Royal Swedish Academy, and is co-chair of the European Academy's Science Advisory Council's study on breakthroughs in sustainable energy supply and consumption by 2050.
Okay, thank you.
So I think we might start straight away, and I'd like to start by asking Steve Chu to give us very briefly his perspective on the outlook for nuclear power in the world or the US, whichever.
Well, it's very personalized country to country. In the United States, it's very personalized state to state. There are four issues.
Is that switched on?
Yes.
Okay.
There are four issues. One is safety, especially after Fukushima. There's a safety concern. There is a proliferation concern. I think some countries who want nuclear may want it to gain access to some of this technology and do a bit of bomb material building on the side, or dirty bomb collection material building on the side. So that's another issue. There's the spent fuel / waste problem. In today's light water reactors, we use about 1% of the energy content of the fuel before it's deemed waste. If you begin to close the fuel cycle, you can get it up to 30, 40, 50%. So that means 30, 40, 50 times more energy per unit of material. Also, if you do it right with fast neutrons, optimized for burn down, you can reduce the storage time by several orders of magnitude. It turns it from a 500,000-year problem into a few hundred to 1,000-year problem. So that is very different, but it requires technologies we have not commercialized successfully yet. Finally, there's the economic cost. The capex of conventional nuclear is about $8 billion per gigawatt, or 1.5 gigawatts, maybe $10 billion, so there's a little economy of scale. Most utility companies, that's a large fraction of their assets. That could be 1/2, 1/3, 1/4 of their total assets. If the reactor is built with a 2-year delay, 4-year delay, and they're not compensated, that's a financial hole they can't get out of. So there are many, many issues. And then finally, I should say that I don't think we will need fission by the end of this century for sure. We're going to transition to other things. Renewables, maybe we can get fusion to work, maybe not, but renewable storage, transmission. So it's not, it's hopefully maybe not in the last quarter of this century, we may not need it. Do I think we need it now, and do I think we should close down nuclear reactors that have 20-year lifetime still in them? No, I think I'll keep them operating safely. So that's quickly.
Thank you very much, Steve. Now, Robert, I know you've thought about public perception of nuclear.
Yes.
So.
Well, what's of course interesting with the whole nuclear issue, apart from the kind of, I would say almost kind of the rationale you just sketched, the four elements, that in the public perception there are various elements that are kind of competing. Safety is one of it, but certainly it's often also placed in the context of energy dependence or independence. The climate change way of looking at nuclear, and then definitely also the cost. And one thing which I find kind of interesting, and it's kind of brought also into light with the Fukushima event, is that you saw countries reacting very differently, and that not all of these reactions are entirely rational, but even you see, for instance, sometimes in certain countries a strong support for nuclear. I think Sweden is a case where you have, it wouldn't be energy dependent so much because there are some other renewables, while countries like Germany, which in some sense have less opportunities, they strongly are against it. And so I think it's very important that if we have a kind of healthy debate about nuclear option, that at least there is a lot of discussion with the public to at least bring the scientific community and the public on the same page in terms of what the arguments that you should address and what kind of conclusions you should draw about. And of course, we have seen that that there's a difference here between kind of risk assessments and actual events happening. I think the public perception really is very much steered by 1 or 2 or 3 events. While I think there's a much deeper discussion there to be held about what exactly is the risk environment and what are the kind of regulatory framework do we need, what is the role of government and all of that. And often this, I notice, is kind of reduced to kind of a caricature in the opinion pages of the newspaper, so to say.
Thank you very much, Elisabeth. I know you have views about the future pathways we should be pursuing.
Yeah, so I think that nuclear power is not cut in stone. It's a research area, research and development. And there are many things that we can make much better. We can have better fission reactors which are not cooled by water. We can take care of the waste by using it again, for example, in transmutation, like Carlo suggested 20 years ago, and is still not commercialized. But we have a lot of energetic waste lying there that we can use. We don't need to take up anything new if we build reactors which can actually use this waste. We can have thorium reactors. We know we have lots of thorium in the world, so we can do a lot of things with the nuclear fission reactors as we have them now. We also, like Stephen said, and like my heart is on the fusion, which Carlo says is terrible, I still think that it will be quite nice, and it will be a renewable also. We can have a combination of fusion and fission, which is also a possibility. So there are many research areas where we can go within the nuclear physics. And it's something that we need to tell, that we are in the research area, and we are, for example, the new fusion experiment that's being built now, ITER, is still an experiment. We haven't built a reactor yet, so we are still in the research. It's not ready yet, but we have many reactors, and I definitely think we should use them. But what we have to do is to get the information properly, because saying, for example, that there will be people saying in Fukushima, 300,000 people died because of Fukushima. It wasn't because of the reactor that things happened there. It could very well be predicted that there would be an earthquake, and at such a large earthquake, there will be a wave. So that was really nothing strange in the whole thing. The reactor had nothing to do with that. But the information has to come out in the proper way, and it's up to us to have a proper education.
Thank you. Carlo, you also have views on the way ahead, I know.
Well, I think I will continue a little bit of what Stephen Chu said about these 4 major questions which are there. I will add another one, which says that essentially after the Fukushima result, after the Fukushima situation, it seems to me that a country like Japan, which was one of the most advanced countries with incredible technology, gets itself into such a mess as what happened at Fukushima times, is an indication that the situation on nuclear power has to be deeply, profoundly revised in order to continue as such. To continue means after finishing up the regular, natural, ordinary closing or whatever activities. No hurry, you don't have to switch everything off tomorrow. But when the new reactor will be needed, they have to be of different nature. Now, they have to be essentially the probabilistic approaches behind all this. Probability means, for instance, if a pump doesn't work, as it happened in Fukushima, you make a second pump, which replaces the first one. If the second one doesn't work, you put a third one. So you reduce the probability to a value which is so low that it seems to be 0. But it's not 0, because the product of a very large accident times a very small probability can give you a signal which is finite anyway, which is not acceptable for many people. So you have to go deterministic. You must be sure that things are done according to such a way that physics law would not allow you to do this. And there are ways of doing this. You have to replace various kinds of things. Now, second problem is there's no more energy from nuclear power than there is energy from fossils. The amount of using this way, it is another point that Chu has mentioned, namely that today we are only using a very small fraction of the nuclear energy. For instance, you take 1 gigawatt electric for 1 year. In order to do it with coal, it takes 3 million tons of coal, which is a hell of a lot of coals, which make 10 million tons of CO2 in the air. So if you go nuclear, ordinary nuclear is 200 tons of uranium that you need in order to get the same results. If you go with thorium, with a well-designed thorium machine, only 1 ton is necessary. Now, most of the thorium is not like the uranium in the sea is on the Earth, and there is a large amount of thorium. So thorium is really quite an interesting alternative, very similar to the alternative from fusion. So since my time is very short, let me mention about fusion. I am not convinced that the fusion chosen with the tritium is a step in the right direction. Because I believe that, first of all, fusion is inducing much higher energy neutrons and many more neutrons. There are 7 times more neutrons per given energy production with fusion than there are with fission. And fission produces 14 MeV neutrons, which are much harder to use than the 2 MeV neutrons which are typically to fusion. So it's a step in the wrong direction. In my view, fusion has to be aneutronic. In my view, the ultimate form of fusion is a fusion in which you no longer have radioactivity, you no longer have radioactive material, no beta, no alpha, only alpha. And there are examples of these things which are perfectly profitable, but they're not studied by anybody, which in my view is the correct direction. There is the example of lithium 7 plus proton, which goes to beryllium 8, which makes 2 alpha particles. This is still a little bit of radioactivity there, but the best solution is boron 11, for which you have plenty, plus proton, which you also plenty, give you 3 alpha particles. These 3 alpha particles produce electricity directly because the alpha particle have a couple of MeV of kinetic energy, which is slowed down electrostatically, and therefore you have a system which has absolutely no radiation at all. So it can be carried in a car or in an airplane, as you mentioned before, because there's no radioactivity at all. It can provide you with a very high efficiency and direct electricity production, as you do in the other system, with about 1.5 to 2 million volts, which is what is needed to produce 1 megawatt for 1 amp of current. So in my view, I think the fusion solution should have less heat exchangers, less gadgets, less materials, and they should concentrate themselves rather on the fundamental fusion. And there are many, many nuclear reactions which are possible with fusion. And if you have fusion, God damn it, you should have no fission fragment, no radioactivity at all. Now, this is essentially my point of view, on the point of view where things should be spent. So I am a little bit antagonistic with respect to the general point of view that you have mentioned.
I mean, Carlo, let me comment on that. I agree with you in principle, but the fusion you're against is incredibly difficult. What you're proposing is even harder.
You haven't tried. I'm sorry. How many hours of your time a day you spend on fusion?
At the moment, I'm not spending time.
So
Cheers. I was for many years. Anyway, let's go to questions now. Who would like to ask? Over here.
Excuse me, you should never say impossible.
No. I don't say it's impossible.
Can you hear me?
Yes.
Yeah, I'm Per. I'm just a random citizen. I have some questions about the thorium reaction. You have talked about it's more abundant, it uses all the energy, and then a couple of other questions. Does it really make less dangerous waste? Yes. Is it less weapon potential? And you don't have to have a pressurized vessel? And my last thing is, did the US make a thorium breeder reactor? But what I've been told is that they made a thorium breeder reactor, but they realized that it could not be used to make nuclear weapons. So therefore they stopped using this.
You want to?
Maybe if the question
is easy.
The question on thorium, I can try to answer. The first question is, the first question you're saying to you, can you make a bomb with thorium? The answer is extremely difficult. Extremely difficult because the uranium-233 is very heavily polluted with thallium-208, which is a very strong radioactive substance, and you produce a huge amount of radioactivity. The general of the military, which is in front of a thermonuclear bomb, will get a little dose in a few minutes of radioactivity. That will not be something. Contact is fundamental for a bomb, and this is not there. Second question you said is about the time, the duration of this radioactivity. There are two elements in radioactivity. One is fission fragments. Fission fragments are dominated by, essentially by elements which have 30 years of lifetime. So as you correctly pointed out, Professor Xu has correctly pointed out, in something like a few hundred years, the whole thing is decayed to a level which is essentially zilch, you can take it out. The second question are the long-lived material. The long-lived material in the case of thorium is uranium-233, which is a perfectly legitimate object, uranium-234, which the oldest uranium are becoming the seeds of the next process. So there is no waste of the actinides, because the actinides becomes the seed for the next activity. The only actinides which are not the seed are the plutonium, but there is only plutonium-238, which is there, the probability 1 part in 10 to the 8, because you have to have 7 neutrons to go from thorium to plutonium-238, and the whole situation is much worse even with 239, with americium, curium, there's nothing of that. So therefore, the materials in the thorium are dominated by the uranium material, which are the seeds of the next system. Now, those seeds are separated in a very simple way, because you know the fluorination is a mechanism which can be allowed in order to extract uranium from other materials just by evaporation. The hexyl fluoride is a gas, and therefore you take out of the gas the seeds, and you put the seeds in the next cycle, and all the rest is essentially dominated by waste, and the waste is mostly fission fragments. In a few years, go away.
Okay. Does anyone on the panel want to say anything about
Well, we
thorium?
just want to make a kind of a correction in the question. The U.S. did not build a thorium reactor. We built a fast neutron reactor. China and India are both looking to building thorium reactors, but they haven't built, as far as I know, they haven't built them because they both have a lot of thorium in their country. But it's again a research project.
I can add also thorium, since we are in Sweden, and I come from Norway. Norway has found a lot of thorium, so that they are also participating, and it has come so far that they are going to put thorium as fuel, test fuel, in their research reactor in Halden. So
Thorium is extremely cheap fuel, $50
Right. We're not
Okay. More questions from the audience? I have one over here. Can we have a microphone?
many questions.
Thank you. I'm Mohammad Moshir Rahman. I'm from Bangladesh. I have just one question, a very small question. How can nuclear power help in a safer ecosystem and reduction in carbon dioxide? That's all.
Simply because it doesn't make any. It's replacing coal. Did I not understand the question?
How can nuclear power help in a safer ecosystem? I mean, I want to mean actually we're using nuclear power for making different devastating weapons. So before this seminar, actually, we are discussing about how can we reduce the energy uses. So my question is related with this. How can we use this nuclear power just to for the safer ecosystem? How can we help? How can we use it, and for the reduction of the carbon dioxide? Yeah.
You understand?
I'm not sure I understand the question, apart from the fact that you're not producing carbon dioxide, so you're using less fossil
Actually,
fuels.
if
the use of the power, it doesn't matter where it comes from, how you use it. Once you've generated electricity, how you use it is...
Actually, I asked a little indirectly. I want to ask you, is it possible to use the nuclear power in a safer way so that the whole planet will be safe in future? That's my question, actually.
Well, I think that's a question that people talked about at the beginning, that it's a problem, but there are safer ways of doing it, Carlo is saying, anyway.
Let me start by first saying, statistically, if you look at how many deaths there are per terawatt hour of electricity generated, including Chernobyl, and making, Fukushima, there could be hundreds of cancers in the future. There's no direct deaths yet. 3 Mile and none even estimated. Chernobyl, several hundred. Okay, you know what the ratio is between that and coal? 6,000 to 1. 6,000 to 1, coal to nuclear, in terms of deaths. And it's going to be much worse because the extreme air pollution of the small particulate matter, 2.5 micron, that is giving respiratory illnesses for young children. So the full impact of that is not even felt yet. Okay? So in terms of safety, there is no comparison.
Yep.
Excuse me.
I mean, air pollution is killing outdoor about 1.3 million people a year out of 60 million deaths. Typically 8 years loss of life. Indoor air pollution about 1.5 million. Those numbers are a nuclear war, not a nuclear accident. And if you ask direct deaths, those are indirect from air pollution. The most dangerous form of power, according to a Swiss study per kilowatt hour, is hydropower. It's breaking dams, drowning people, and accidents in construction of dams.
May I just add a little bit to what you say? First of all, let me give you two factors. Every second, 18 people die on Earth and 20 are born. The difference of 2 per second makes the population explosions, which is 80 million per year, 1 billion every decade. These are the numbers you're looking at. Compared to those numbers, obviously what you're talking about is an absolutely negligible element, respect to 20 per second. However, you should not look at this as a number. You should ask yourself, what is the population thinking? When you go to Germany, I don't think there has been any single serious accident in Germany. But if you ask any German citizen, do you want nuclear? It says, no, nein, danke. This is a fact. So there are factors which have nothing to do with a simple risk analysis story, which has to do with the way in which people, especially the voters, feel to decide on something. And this something has to be taken into account. Thanks God, this is not a question of death of life, but it's certainly a question of opinion. And the opinion making is fundamental when it takes to get somewhere with one solution rather than the other.
I think, sorry, Steve.
I also want to add, even with their existing fleet, what we learned in Fukushima, there are some lessons learned there. For example, those reactors were cut off from their water supply, they were cut off from the electricity supply. In California, we have nuclear reactors, and in a major earthquake, you can expect to be cut off from your electricity and your water. And so there's a big water reservoir sitting above in those reactors. So for the first day or two, you can cool those reactors. The first day or two are the most critical. Another lesson we learned in Fukushima is the operator training wasn't as deep as we thought it was. It turned out that, in the United States after 3 Mile Island, we do a lot of simulator training, but in addition to that, they have the authority to do things in that reactor. You can't radio to the head of TEPCO, the utility company, or the Japanese government to ask for permission to do something. You have to be reacting much more quickly. And in Japan, they did not have that. They would have to go up the chain, and then the higher up the chain you go, except in occasional circumstances, the least knowledgeable you become. And imagine you're an airline pilot and United Airlines, and then your engine stalls at 40,000 feet. You do not want to be radioing the CEO of United Airlines to ask what to do. So similarly, in reactor training, the operators on site have to know what to do. They can be drilled on simulations out the wazoo, just as airline pilots have done. We learned a lot of things. One final, this is actually no expense. This is very low budget. Finally, what we learned is that there were appallingly few sensors in those reactors when they went way off normal. And so for the first month of Fukushima, I spent a lot of time. There was a little crew of working with me. We're trying to help the government. We didn't know what the pH was in the reactor pressure vessel. We didn't know what the hydrogen content was. We did lots of calculations, but there were only calculations. There was nothing that allowed us to get in and get a sample of what was going on. And you're pouring salt water in, you're evaporating the water, and it's getting more salty. We can only do a calculation. It's when the salt would precipitate so much you couldn't cool it anymore, and you'd get a melt through. You can redesign the reactors today to go and get a little biopsy, if you will. We crawled around a decommissioning reactor of the same design. You'd have to bleed it out in a line, but you'd have to bleed for many, many hours in order to get a clean sample out of a thin line. Okay, so even things like that, sensors, the cooling pool, there was no sensor that tells you when the water, how deep the water was beyond the normal operating level. You can actually have hydraulic tube that goes down to the bottom. You know what the density of water is. You can bring it out. It doesn't even have to be electrical readout. There was none of that. There was no yardstick that tells you how deep the water was. So you can have a lot of very inexpensive, redundant measurements of once it goes off normal, so that we can, in other words, we're just doing calculations. And as an experimentalist, man, I felt really queasy about lots of calculations. I wanted real data. Is there really, one of the spent fuel pools, was there really water? And so the existing fleet can be made much safer, and the training can be made much better.
As a theorist, I feel even more queasy about calculations. Carlo, very briefly, because we have a lot of questions.
First of all, let me say that the Fukushima had one anticipation in 3 Mile Island. 3 Mile Island and Fukushima got similar situation. Second point is, you cannot assume that no error are possible. Errors are possible, you recognize errors, and you have to accept that anything may have errors. So the fact that you say that this was an error here, this was an error there, and so forth and so on, is fine with me. But it doesn't tell me that error have to be prevented in absolute sense. So there will always be some error somewhere. So an errorless system, it's certainly something which is very hard to accept by human people. Give you a measured error. One load in a reactor is 10 to the 10 sieverts. 10 to the 10 sieverts are contained in a reactor. And 5 sieverts is a 50% killing capability. So we are talking about reductions in the radioactivity, which is 10 orders of magnitude, 15 orders of magnitude, respect what it is. When we're talking about this, the possibility of an error coming from mistakes, from this and that, is possible. It has to be accepted. So you have to accept life with errors. Life without error doesn't exist.
It's dangerous. We have to treat it very carefully. Question over here.
That's not my point.
But not as dangerous as other things.
Isadora Vronsky from Greenpeace. So I have a question that I asked in the previous nuclear session, which is, with commercially available technology, not thorium reactors, are we able to use nuclear power that currently make up 6% of primary energy demand to reduce or phase out over 80% of fossil fuels in the time scale given by IPCC or International Energy Agency? Do you see that as realistic? That's the first question. Second question is, what happens with the inflexible base load that nuclear make up when we get other countries that phase in a lot of fluctuating renewable energy? Can, for instance, France 58 reactors be an obstacle for Germany in the energy vendor? Are we choosing between different energy systems where the base load is putting a cap to how much renewable energy we can put into the system?
Okay, so the first question, have we commercially available build nuclear reactor to reduce fossil fuels significantly or to a large extent, if I understood the question, in time?
Well, maybe I can start a little bit of saying we are building reactors, very many reactors over the world today. What we have very close to us here in Sweden is these reactors in Finland, where they have tried to go with new designs, and one can say that every new reactor you put more and more safety requirements, which also makes them take longer and longer time. It's a new reactor every time, you can say. But for example, in US, they have had many plans of building smaller reactors, which could be done in 5 years. In England, they have decided to build reactors now, which will be delivered by the French company, and that will also be built in time. And I think that also for the reactor places where we have, that it is, we can upgrade the reactors very much like we are in Sweden. So the question there is to replace the fossil. This is for producing the electricity. So, you know, if you think about the whole world, I can probably not say yes at all to this. If you think about Sweden, I don't think that we can replace the nuclear power we have today with something which is fossil-free. We would have to go with gas or something in Sweden. So the nuclear power that we have, we should really take care of and use.
Let me make a slightly different answer. I think to have a real crash development of nuclear, if somebody wanted to do that, in Europe anyway, the constraint in the Western world would be manpower, because there's been a pause on nuclear buildup for so long. There aren't the skills there, maybe different in Asia. I mean, that can be repaired in time, but if you wanted to start immediately, it'd be difficult. Now, the second question?
What was the second question?
Who can remember the... yes, the role of nuclear, if we have a lot of renewables, you know, how do we reconcile the... I mean...
Well, look, that's you know the answer to that.
Yeah, I do.
You bring up nuclear and you keep it steady. It's a very steady source. It's baseload. Hydro and gas can interface very well with renewables. Right. They're the ones that have the real rapid response.
But in some sense,
the question was rather whether baseload creates a problem for when we start to get really high amounts of renewable share in the electricity system. So we get a system conflict
Right.
because we cannot.
I think we're a long way
like
from
the
that.
border between France and Germany in the future to come, for instance.
Perhaps may I say
yes,
something?
if it's quick, Carl.
Yes, well, we're all quick. I pitch faster. But anyway, we have taken some time to understand this kind of question. There is no doubt that the variability of the renewable energies are a serious problem. This is both true for solar, but it's most important for wind. Wind is going like a cube of the velocity of the wind. The speed of wind is going up by a factor 2. The amount of energy transported goes up by a factor 8, and so forth and so on. So some situations you have a lot of energy, too much energy. In some other cases you have not enough energy. So paradoxically, the answer of the future to this is coming from the energy storage, which of course in case of nuclear is already guaranteed because nuclear can run all the time. Now, I don't believe that storage based on batteries, it's going to be sufficiently careful in order to solve in a conservative way all the problems we have. I have enough problem to get my little thing here, a telephone running all the time because every day it's discharging itself. If I have to have a car, my house, and everything else on this, I'll be in trouble, independently of the cost. Now, I believe that the solution will come if you can transport electricity into fossils, for instance, methanol, and then go back to methanol, back to electricity again. This is possible with fuel cells. A fuel cell is sufficiently efficient, so you can take fuel cells energy from electricity to chemical, and from chemical back to electricity with a gain which is almost a factor 2, which is an acceptable number in a chain of reactions. So in my view, the answer for the future of renewable, the continuity of renewable at high level of consumption, as is proposed, for instance, in Denmark, where one says we will only have renewable by 2050, is justified only if you can solve the problem with storage. And the only thing I know about is which can work on storage is fuel cells.
We have a question here from Twitter, I think. Can you read out the question?
What steps do you think the scientific community can make to help remove the fear and stigma from nuclear power?
Robbert, do you want to answer that?
Well, first of all, I think we had some terrific examples here of the various kind of risks that we run. And I think this is really very basic science. You don't need an advanced degree to understand that. I think, you know, we could, at elementary school level or something, you can already educate children about the risks that are all around us. And so I think actually education is absolutely key in this. I think also it's important that we keep on emphasizing that there are risks associated. I think in Japan, one of the problems was there was like this myth of 100% safety, which led not to the kind of improvements you were just suggesting, small things to mitigate these risks. But I would say absolutely key to this is start early and broadly by educating people with these kind of risks.
Elisabeth?
Yeah, I would also like to take up some point is the word nuclear. You know, when we go to the hospital, then NMR is now called MR. So suddenly people think that it is X-rays or something. There is no reason for us to take a word the word nuclear. And why is it taken away? Because just they think that people get scared of the word nuclear? No, so we should just be clear about it, educated about it. It isn't dangerous, right?
I'll just tell you a little anecdote. The first application to make a hydrogen filling station for cars in East London, there was an objection to the application on the grounds we don't want hydrogen, that's what they make hydrogen bombs out of. I mean, that's what people think, it's a problem. I have a question. We can take 2 more questions, I think. We're over time. We take one here. And then maybe there was one back there. Yeah.
I have a question about insurance for nuclear plants in countries with small fleets of nuclear plants.
Small what?
With small fleets, with few reactors, how is that handled?
What is the question is, how is insurance for reactors handled in countries which have a small fleet of nuclear reactors?
Oh, that's a very good question.
I know, but we don't know the answer, do we?
Well, I think I know the problem.
Even you don't know the answer, Carlo.
May I try to answer your question?
Yes, if you're brief.
At present moment, every country receives the waste, and the waste is remaining in the country where the waste was. Now, if large countries can solve their problem, for instance, US, France, Germany, UK, what is going to happen if a small country will produce waste, and then the waste has to be put somewhere with a system? There will be a major problem in solving this situation. So I believe, at least in Europe, where there are so many different countries and small countries, a European common effort in trying to decide to have one common repository for all these materials should be taken. Now, ideas of doing that came to Russia about 10 years ago when Adamov was in minister. At that time, the willing was that Siberia had enough area, space to take enough radioactivity, for instance, from Albania. I'll give you an example just like that, and brought it there, and there would be no problem. But indeed, the Duma in the Russian parliament has refused such a possibility. Similar argument applied also about Australia. Yes. Also, Australians argue that there is plenty of space in Australia where you could safely put away a significant amount of radioactivity, especially small amount for delicate small countries don't have the critical mass to be able to solve the problem by themselves. But also that one has been turned down by the decisions of the parliament. It seems to me that is an open question. It's a big problem, as you are corrected, but there's no moment a solution, which is acceptable.
I mean, let me just comment on the Australian situation. Australia is the 2nd biggest exporter of uranium in the world, but they won't have nuclear power themselves. It's really hypocritical.
I think your question was insurance vis-a-vis safety and things of that nature.
Yeah.
So the best insurance, you start with proper training, risk mitigation. Think about airlines. There's an international standard if you allow airlines to land in, let's say, the United States. There's an insistence that the pilots have a certain level of training, even if it's from a foreign airline. There's an air certification issue. Not every country can just willy-nilly throw up a plane, and so countries will say these airplanes would have to be certified if they too want to come into my airspace. They're very similar situation has to exist with nuclear power because, you know, the contamination could actually go into an adjacent country as well as the own country. So before a small country begins to get nuclear energy and nuclear power, this has been a big debate within the United States. I was saying that before the United States actually exports some of this technology, we have to make sure those countries have the infrastructure that can train the operators and can do all those other things. Otherwise, it would be irresponsible for a Westinghouse to be selling nuclear reactors to a small country like a Jordan or Vietnam or et cetera, unless you had that. And so I think internationally, those people who might think of exporting nuclear technology, whether it be Japan or Korea or China or the US or France, have to be all together on this. A nuclear accident anywhere in the world affects the entire industry. And so you start with that. It's not after it happens who's going to pay for it. That too is important, but boy, you can mitigate the probability of it happening by a lot. And that's what we need to do.
Thank you. We're way out of time, but I did promise to take a question back there. We will take this one last question. Can you make it relatively quick, brief? They told me to finish at past. Maybe my watch is fast.
Thank you. When we look at, say, molten salt reactors, we know that they are deterministically safe and not probabilistically safe, as Professor Rubbia said, but still they're not being implemented. And there are lots of these improvements for nuclear reactors, like molten salt, thorium, fusion even further away, that are not commercially being utilized? Is it because they are still in research and they are very hard to realize, and is there another way in which we can accelerate this development?
Elisabeth, would you like to take that?
Yeah, I think that we really need to have the public approval of this energy system, and I think that this session really shows what we need to have. We need to have a lot of meetings talking, not only the education in the lower school. I know when we arrange a nuclear power meeting in Stockholm, it's not people coming asking questions, then it's only the people who know everything who comes and we discuss how to improve. But we don't have this general communication that we really need, and I think that's what's really needed, because there are research is there, and we even have things which are ready for testing. I mean, that even Carlo could talk about, right? So that it is there, but we don't get the public, or even we don't get the money. Like we say, there is no money for it because the money goes to the wind or something, which we don't need today. We need this.
There's another
Steve?
There's another issue in the reactors you're talking about. For example, we know in a plutonium metal reactor, you just it's inherently safe. You walk away from it, and we know it doesn't melt down. There was a demo prototype reactor made in the United States that did this. But there's another issue, and that has to do with the proliferation issue, and which is why that work was stopped. And this is also the questions raised. I'm not saying whether I agree or disagree. I'm just saying the other side of this is that in fast neutron reactors, you can breed them for maximally burning down the long-lived actinides, which are a real spent fuel problem. But you're also making out of U-2, you're making plutonium, fissionable plutonium out of U-238, which is capturing the energy content. But you can produce more fissile material this way, and so that's the other side of this that has been in play for the last half century.
So we're almost 10 minutes over time. There's another session beginning shortly, so I'm afraid we have to end it there. And please thank the panel again and the audience.